The issue is with yeah, honestly, because I
That's why we
yeah, because then I can go locally and use the strength from this on reps.
Yeah, well, you like you could put on like sets off.
I might just try to use my that way you have. So maybe it's written, but every case, so if it works, you get so you have very nice.
But ours is more accurate.
I have a flash one. I see, right? It's very done. If you get the rest.
Yeah, so, and then.
How's your gender?
Oh, for the. For wash bottle, yeah.
Yeah.
You always dry.
The red?
No, it's just, it doesn't, no, it shouldn't. Probably the cheapest one they sell, like the clear is kind of more. Is it similar? It's similar to.
Yeah, we did.
I'm not sure if
Well, I mean, the difference was like ours was in the category.
He said that this.
Yeah, that's the thing, we're not gonna follow.
It's more solid.
Ours is kind of like entertain.
More accurate.
Yeah, so you got your one right now. We didn't do that. Yeah, you're the only entertainment.
But we can get the
You
right.
can get free money.
Also, what they said is for the yeah, it's only.
The only difference for
Change
us
the color,
is
it's
since
like-
ours is medical. You know,
No, just because afterwards. That's how they do it. There's only guys in there. And that's a whole other machine and like a whole other thing. Yeah, they always something get into Disney.
I thought, no, they hired berries.
Oh, so you don't have color stuff for the.
Maybe I should apply to them.
Why not?
I don't know.
You could just, what you could do.
Give it a shot.
Like,
I don't think ours is, you know.
You guys could win some money.
No, it's weird. We're in a weird spot.
You're gonna have all.
I don't understand, like we use, yeah, because we're also government, like,
Yeah, because we.
I don't think it's, yeah, we're not gonna do
Next to that is.
maybe.
Yeah, I think the recommend is just projects. That's how that's the mindset I have into this.
Yeah, but. They came in the first day and said, well, I need to be doing this decision, I want it. I'm like,
Yeah, exactly. No, I think for, it's the. I forgot the word. It's the construction agreement. Basically, this is something, I did this in, which is pretty much, everything that you're doing is like. And anything.
stop. Disease and we are more crazy than
Be like that.
We don't know. Guys. Yeah. And they asked about it was not.
What's up?
Question.
Sure.
Yeah.
So for the homework, I know you did go in class, but in the code where it says solution and current solution mix, is that where you place the equation that you discretized, or?
No, so the equation that you discretize, like, coefficients for that go into the matrix, just like that goes out. So for the sole current and sole next, that's where you basically make the exchange between phi and plus one phi n. So you're basically keeping track of both every time. So, and so phi n, remember, that's sole current. And so that's you also need to use that in the equations as well. And then after you solve for sole next, then we do update that. So any line that involves sole current and sole next, kind of on the first part of the line, they're usually very short. You're either updating the current solution, or you're solving for the next solution using the main system.
Yeah, just double check. It was a really good. Oh, wait.
People order to I can go pick it up. Yeah. Let me just- So I thought if I pulled off kind of on the screen. Oh shit. Get it. That's true.
All right, it's 5:30. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Last day before spring break, so it's an exciting day. After this, you guys don't have to see me for 12 days, so that's probably a good thing for you guys, right? Okay, so today we're actually starting something new today, and so we are learning something called the finite volume method today, right? So as of Monday, we're officially done, except for one thing that we'll do later, but we're basically officially done with the finite difference method. So we're pretty much closing the chapter on kind of one big area of our class. Right? So today, we're starting kind of the second half of the class, which has to do which is finite volumes. Okay, and so we'll go over this in a bit. But finite volumes is basically just another parallel technique to finite differences. And so what you'll see is that the second half of the class is going to pretty much mimic. I try to say mimic and mirror at the same time. Basically, going to mirror our first half of the class. And so everything, basically the same path that we took for finite differences, we're going to do with finite volumes. So today we're going to introduce just the concept of finite volumes, what it is, how it's different from finite differences. And then when we come back from spring break, we're going to do diffusion, we're going to do convection, we're gonna do unsteady problems, you know, all the same, basically the exact same path, but everything with finite volumes, okay? So finite volumes is exciting because, you know, a lot of, I would say, a lot of pretty well-respected codes out there use the finite volume method. So some of you may be familiar with codes like OpenFOAM. So OpenFOAM is one of the more famous finite volume codes. And so, you know, my hope is that after this section of the course, you know, you'll be able to understand how those codes work a little bit better, okay? All right, so some announcements. Remember, homework 4 is out there, and homework 4 is due this Sunday. So make sure you get it in before the deadline. I'll be grading it over spring break, and so, you know, if you get it in on Sunday, then, you know, I'll be able to get your grade before you come back. Okay. And then the next homework assignment is not going to come until after spring break. So after Sunday, you won't have to worry about this class until we come back. Yeah, question. Yes, yeah. Basically same as usual. So whenever, as soon as I grade it, I'll put the solutions up for it. Yeah. All right. So I think that's all my announcements. Are there any other questions I can answer before we get started for today? Okay. All right. So let's go get started. And so the topic for today is the finite volume method. All right, so just like I mentioned, you know, earlier today, you know, we're pretty much all done with the finite difference method now. So we've covered most 95% of what there is to know about finite differences. Okay, and so we're going to be learning a new technique. And so the finite volume method is really just kind of another method or another approach to solving these kinds of differential equations. Okay? Okay. And so just like we saw with finite differences, we're going to be solving differential equations. So that part's not going to change. And we're going to be developing computational algorithms based. Okay. And so, you know, we're just going to arrive at our code. We're going to arrive at our equations in a slightly different way. Okay. The big difference is this. And so in finite differences, that our main focus was on the nodes or the points in our grid. Okay. We solve our equations, or when we solve our linear system in finite differences, we solve for the solution values at those grid points. And so if we had a two-dimensional case right here, our focus was on all of these grid points, right? And so we would label the grid points, we'd give them ID numbers, we'd give them IJ, so on and so forth. Okay. Too many grid points. So the grid points were the focus, right? So we solve for the solutions at these points. Okay. And what you'll see is that finite differences makes some things really convenient. And so one thing that's convenient about finite differences is that the boundary conditions are applied directly on the nodes because your nodes or your grid points are sitting right on the boundaries. Okay. Okay, so that's finite differences. Okay. In contrast, we're going to be focusing on finite volumes. And so in finite volumes, instead of focusing on the grid points, what we're going to be focusing on are the actual, I would say, spaces in the grid. Okay. I'm very tempted to call them elements because I come from a finite element background, but in reality, they're called cells. Okay. So it looks something like this. So let me draw a 2D case again. I'm not going to draw as many grid points this time. Okay. And so what we're interested in finite volumes is we're going to be solving for the solutions inside these cells. Okay. And so what you'll see is that, our grid, we're going to draw it the same way, except instead of labeling the nodes, okay, so on finite difference, we label the nodes. Instead here, we're going to be labeling the cells. Okay, so there's going to be cell 1, there's going to be cell 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so when we solve for the solutions in finite volumes, that solution is going to be valid over that entire cell. Okay, so it's a slightly different kind of way of thinking about it, right? And it's going to take a while to get used to, just because we've done basically 2 months of finite differences, talking about the nodes, and so doing finite volumes is a little bit of a shift. Okay, and the biggest difference that you'll see is that applying the boundary conditions are going to be different, because the cells, we have cells that are on the boundary, but when we're talking about the cell kind of as a whole, the interior of the cell is not on the boundary. Okay? So for now, I'll just leave a note that applying boundary conditions will be different. Actually, let me give you an example of a 1D case too, because thinking of a cell in 1D is a little bit strange. And so our typical 1D grid, might look something like this. And so we have kind of a segmented line. Okay. When I'm talking about a cell in 1D, I'm talking about kind of the space in between the cells, right? And so it would be something like this. Right. And so hence that's where the method kind of gets its name. So, the volumes, finite volumes, refers to the cells in our grid. Okay. And if you're wondering kind of where finite volumes is most applied, finite volumes has a lot of very nice properties compared to finite differences. Most notably, it has very nice conservation properties. And so that makes it very, very nice for simulating things like fluids phenomenon and heat transfer as well. Okay. And so, like I mentioned earlier, if you've heard of the software called OpenFOAM, OpenFOAM is one of the more famous finite volume codes out there. So I'm gonna try to make it so, you know, I'm gonna try to make it so that we can cover a little bit of open foam at the end of class, at the end of the semester. You know, but we do have to kind of pick it up a little bit so that we can get there. But that's what finite volumes is mostly for. Okay, any questions on this so far? Okay. All right, so that's kind of finite volumes in a nutshell, or kind of where, you know, how it kind of works. And so you may be wondering, you know, what's going to be the big difference, right? So if we're focusing on the cells instead of the points, you know, how is this going to affect our derivations? How is this going to affect our methods? So finite volumes and finite differences share one very kind of important property, in that the goal is still the same. And so what I mean by that is that, you know, remember, whenever we're solving these kinds of problems, we're starting with a differential equation. And when we apply the finite volume method, our goal is to take that differential equation and turn it into an algebraic set of equations. Okay. So that's really the goal of almost any computational method. Because if you can get a problem that you can formulate it as an algebra problem, even with a lot of equations. And so, you know, we've seen situations so far with finite differences where we have, you know, maybe like 1,000 equations and 1,000 unknowns, right? But that's fine. And so, you know, the nice thing about using computers is that, you know, computers are very good at algebra. And so if you can transform any system, you know, not just differential equations, into an algebraic system, your computer will be able to help you out a lot with that. Okay. The difference here for finite volumes is how we arrive at this algebraic system of equations. What you'll see is that the main difference here is that, you know, because we're dealing with these cells instead of the points, you know, this kind of lets us use a new mathematical tool at our disposal, which is integration. All right, any questions on this so far? Okay. All right, and so for the rest of today, you know, we're going to be going over the main, I would say, mathematical tools that we need to apply the finite volume method. Okay. And so some of this may be review. Hopefully it's review from classes maybe like 3 or 8. But I'm probably some of this is also going to be new as well. Okay. All right, so let's start with probably the most important theorem that we're going to use in finite volumes, which is the divergence theorem. Okay. So the idea with the divergence theorem is that it lets us transform an integral, an integral in one form to an integral in another form. Okay. Okay. in particular, the two types of integrals that we're going to be converting between is one, which I'll call a region integral, and another, which I'll call a boundary integral. Okay? And so I'm using that terminology because the divergence theorem has versions, has a 1D version, it has a 2D version, and a 3D version. Okay. And so it's I can't just say convert a double integral to a line integral, right? Because it's gonna take a slightly different form in 3D and 2D. Okay, so let me write out all three forms here. So let's start with the 3D one. We're not actually going to use this one because we're not doing any three-dimensional simulations. But traditionally, the divergence theorem is presented as a 3D theorem, okay, if you see it in a math class. All right, so it works like this. And so on one side of the equal sign, we have a triple integral over some volume V. We're going to take the divergence, some vector field. Let me call it F, actually. dV. And this is equal to a closed surface integral over the boundary of V, okay, of the vector field dot product with the normal vector. We have a triple integral we have a surface integral around the boundary of V. We typically call partial. Okay. Let me draw this out for you because it's a little bit kind of hard to visualize just from this equation here. And so let's say we have a three-dimensional object. So let me draw a cube. And so in our cube, the volume occupied by this cube, we'll call that the volume V. Okay. Okay. Whereas kind of the shell around this cube, and so you can think of like the exterior of the cube. Okay. We'll call that delta V. Okay. All right, so this is the divergence theorem. And so on the left-hand side, you can see we have that triple integral over the volume V. I call this the region integral, okay? Because we're integrating over the entire region of the volume V. And the surface integral, since that only acts on just the exterior of our volume, I call this the boundary integral. All right, so that's the basic idea of divergence theorem, is that if we have some kind of region integral of the divergence of a vector field, this is going to be equal to the surface integral over that same region of that vector field dot product with the normal vector. It's a little bit hard to draw in 3D. I do the 3D one first just because you might maybe you remember this from 308 or something like that, or 258. But the ones we're going to use mostly in this class are the 2D version and the 1D version. You've probably never heard of a 1D divergence theorem because it's actually a little bit silly, but we'll kind of get there when we get there. Okay, any questions on this so far? Okay. All right, so let's look at the 2D version. So this is the one we'll probably use most often in this class. All right, so it's going to have the same idea, so same concept. And so on the left-hand side, we're going to have a region integral. And on the right-hand side, we're going to have a boundary integral. It's just what is defined as a region versus a boundary is different in 2D. Okay. All right, so for the region integral, for a 2D region, that is going to be a double integral over some area A of the divergence of some vector field F. This is equal to a line integral F dot product with N ds. So on the left-hand side here, we have a region integral. Right here we have a boundary integral. And on the right-hand side, we have, it's basically a line integral. So it's going to be a line integral around the boundary of A. Okay. All right, so let me go ahead and draw this for you, just like above. This one's a lot easier to draw. So let's say we have a square. Coincidentally, the square is going to be the most common finite volume that we're going to be working with, just due to simplicity. Okay. And so A is given by the region on the interior. Okay, so the area that's occupied by this square is given by A. And then around the boundary, let's say that we traverse around the boundary in a clockwise fashion. Okay. The boundary is going to be given by partial A. So divergence theorem lets us kind of transform between these two integrals, right? And so if we kind of start with the region integral, we can transform it into an integral around the boundaries, okay? Or if we start with the boundary integral, we can transform it into a region integral. Okay? The reason we do this is that eventually when we use this and we integrate our governing equations over our cell, it's going to be easier to evaluate one type of integral to another, okay? And so we use the divergence theorem mostly to transform our integrals into something that's easier to compute. And you'll see what I mean kind of once we actually apply this. Any questions on this so far? Okay. All right, so let's do the 1D version. The 1D version is very silly. You probably never heard of 1D divergence theorem because 1D divergence theorem is just taking the integral. Okay, so 1D divergence theorem, we have integral from A to B. So the 1D version of the divergence would just be the derivative. And so we take the integral from A to B along the line from A to B of d phi dx. Okay. And so we don't have to use any kind of fancy theorem for this. We can see that, this dx's are going to cancel out. And so we have integral from a to b of d phi. Okay. That is just, phi by itself. So phi of b minus phi of a. Okay. So there's really no such thing as 1D divergence theorem. 1D divergence theorem is just doing the damn integral. Okay. But this one's going to be important because we're, of course, when we start to apply this, we're going to start with 1D problems. And so this one's going to be helpful. But it's also helpful to kind of remember when you take an integral of something and you're integrating over the same variable as the derivative, then you can just cancel out the derivative with the integral and just apply the function itself. All right. All right, so the reason I'm bringing this up is the way the finite volume method works is that we're going to take our governing equation. And so we're going to take our equation that has our unsteady term, our diffusion term, our convection term, and our source, and we're going to be integrating that over the cell. Okay. So that's really the key. Okay, so let me show you how it works in 1D. And so in 1D, let me go ahead and label all these nodes. So each of these nodes have a certain location. And so let's assume that we know all of their locations. So we have x1, x2, x3, x4, x5, x6. Okay. And then we also want to solve this equation. So we have partial phi, partial t, plus u, partial phi, partial x is equal to k, partial squared phi, partial x squared, plus q of x. Okay. So this right here is our governing equation. It has all of our usual suspects. And so there's partial phi, partial t. This is unsteady. The unsteady term. This is our convection term. This k, partial squared phi, partial x squared. This is our diffusion term. Of x, this is our source term. And so if we were solving this with finite differences, if we were solving this kind of with our usual way, we would take this equation here and replace all the derivatives with finite difference, right? That was kind of our kind of MO for the first part of the class. Okay, we're not going to do that anymore, and so we're going to be applying finite volumes, and so what we're going to be doing instead is we're going to be integrating. Remember, because integration is linear, we can integrate each of these terms separately, right? So we're going to have 4 integrals here. We're going to have an integral over the unsteady term. We're going to have an integral over the convection term, one for diffusion and one for source. And just for the sake of kind of filling this in, let's assume that we're integrating over the first cell. So we're integrating from x1 to x2. Okay. All right, so we'll be applying this integral to every term in our equation. Okay. And since we're integrating from x1 to x2, that means we're mostly concerning ourselves with this first cell. And so this first cell kind of exists between x1 and x2. Okay. And so this is kind of the starting point for finite volumes. We're not going to take it all the way today because that's going to be the subject for the next few weeks. But I kind of wanted to give you a preview of kind of where we're going. And so the way that the divergence theorem comes in is that we're going to apply the divergence theorem to every term here that has an x derivative inside the integral. Okay. And so we're mainly going to be applying it to this term and to this term. So these terms apply divergence theorem. To simplify the integrals. I say simplify, I'm going to put it in quotes. What you'll see is that in 2D, it's not going to make it all that simpler. In fact, you may think that it's actually making it more complicated, but it's a necessary step. So it's a necessary step in order for us to get the equations that we need to from finite volumes. Okay. Any questions on this so far? Yeah.
I was curious about the cells, like, so the cell, when you go up the one, is that just the cell being the line?
Exactly. Yeah. So I make it a little bit thicker here just to emphasize it, but the 1D cell is just the line segment between x1 and x2. Yeah, it's definitely easier to visualize in 2D and 3D where it actually has like area or volume. But yeah, but 1D finite volumes technically does exist too. All right, any other questions on this? Okay. All right, and so I'm gonna leave those two terms alone, right? And so the convection and the diffusion terms, we'll kind of save that for later. But you can see that we have other terms in our expression. So we have this term, the unsteady term, and the source term, right? So we have these integrals that we need to evaluate, but we can't really apply our divergence theorem here because it doesn't really quite fit the model. Okay? You may be wondering, why can't we apply divergence theorem to the unsteady term? Well, that derivative is in t, it's not in x. And so, we have to treat that one a little bit differently. And so to evaluate these integrals here in red, we need one more tool for us to evaluate these integrals. And that is known as the trapezoidal rule. Okay, so the trapezoidal rule, it's a neat little trick. And so if you haven't seen it before, you're going to look at it and see, you're going to ask yourself, where was this my whole life, right? So trapezoidal rule is kind of a trick that you can use to quickly evaluate an integral without having to perform any kind of antiderivative. And so, I think most people would agree kind of the most painful part of performing any kind of integral is the antiderivative part, right? So you have the integrand, you have to take its antiderivative in order for you to evaluate that integral, okay? The trapezoidal rule works only in the case when you have an explicit expression for the integrand. Okay? And so you're going to look at the trapezoidal rule and you're going to wonder, why don't we just apply this to everything? It's so simple. Well, because the convection and the diffusion integrals are a little more complicated, we don't have an explicit expression for the phi function. That's actually what we're solving for. We can't apply it to those ones, at least not directly. Okay? We're going to apply it kind of in its own way once we get to 2D, but it's not exactly the same thing. And so the trapezoidal rule looks like this. And so let's say, I'll show you the 3D version first. No, we're not going to use it, but traditionally this is presented in 3D usually. And so in 3D, let's say that you have a triple integral of some function, and this function is a function of x, y, and z. Let's say that, just like above, we're evaluating this triple integral over some volume V, okay? Where, I think the easiest volume to draw is just a box. Okay. So what the trapezoidal rule says is that you can compute this integral. You don't have to perform any antiderivatives at all. All you have to do is you just have to take the integrand. And so our integrand here is just our function f. Okay. What you're going to do is you're going to evaluate the function f at the centroid. At the centroid of your domain V, and you're going to multiply by the volume of V as well. Okay. So that XC, YC, and ZC, that is actually very significant. So if we draw kind of a point kind of in the middle of our region here, so this is XC, YC, ZC. Okay. This is the centroid integration region. Okay. And I just noticed, I chose kind of unfortunate notation, but this V here, okay, this V here specifically is the volume of our integration region. And so to perform the trapezoidal rule, you take your integrand, you evaluate it at the centroid, and then you just multiply by the volume of the domain. Okay. No antiderivatives necessary. It's very, very, very simple. And so this is particularly nice because eventually, with the finite volumes, just like we did with finite differences, we're going to be writing code involving finite volumes, right? And so performing antiderivatives and performing integrals is something that code at this point is not very good at, okay? At least not MATLAB, right? And so if we're going to have integrals in our expressions here, that's going to be difficult for the computer to handle. But if we evaluate the integrals using the trapezoidal rule, we don't have to perform any antiderivatives. We can just evaluate the integrand, and that's going to be a lot easier for us to code. Okay, so this is very much kind of a coding convenience for us. All right, let's look at the 2D version. And so the 2D version, we have double integral over some area A of some function x and y, dA. And so what the trapezoidal rule says is that we can evaluate this integral without having to perform any antiderivatives by just evaluating our function at the centroid, multiply by the area of the region. So once again, this A here, area. Okay. There's a 1D version as well. Not as helpful, but it is helpful. Okay. And so for the 1D region or 1D version, let's say we have an integral from a to b of some function f of x dx. Okay. Normally, this isn't an issue, but it is an issue for code. Okay. And so if we were to evaluate this integral, we take f of xc times the length of the region. Okay. And so the length of this region is b minus a. B minus a right here. I have a couple examples here to kind of show you how this works. Because if you've never seen trapezoidal rule before, this looks like voodoo magic, right? So you might be saying, how can you say that we are performing an integral without actually performing the integral? So I'll show you in a second how this works. Actually, if you're familiar with the concept of a Riemann sum, if you remember that back way back when you were learning calculus, this is very similar, except it's a very simplified version of the Riemann sum. Okay. All right, any questions on this before we do a couple examples? Okay, all right, so let's do a couple examples. I'll do a 1D example and then I'll do a 2D example. Just to prove to you that it works. Okay, so let's evaluate this integral. And so we'll take the integral from 6 to 10 of the function 4x plus 6 dx. Okay. And we want to evaluate its value. So I'm going to evaluate it using the normal way. So I'll take the antiderivative and then apply the integration bounds. But then we'll also evaluate it using the trapezoidal rule as well. Okay. I'll show you that in this case, they actually end up being the same thing. Okay, so let's evaluate normally first. Okay. So integral from 6 to 10 of 4x plus 6 dx. Okay. But first, I'm going to take the antiderivative. And so the antiderivative of 4x is going to be 2x squared. The antiderivative of 6 is going to be 6x. Okay. We're going to evaluate this between 6 and 10. We're going to evaluate this at the integration bounds. And so we're going to have 2 times 10 squared plus 6 times 10. Okay. We're going to subtract out the other integration bounds. So minus 2 times 6 squared plus 6 times 6. Okay. Okay, and so if we evaluate that, we plug in the numbers you can punch into your calculator, you get a value of 152. Okay. And so the true value of this integral is 152. And we evaluated that using the normal, kind of the normal way of performing integrals. Okay. Let me do the same thing, but let's use the trapezoidal rule. And so to evaluate with trapezoidal rule, we need a few pieces of information. Okay. First, we need the integrand. And so when I say integrand, I just mean whatever the function is inside the integral. Okay. And so here's just a function of x. And so it's going to be 4x plus 6. Okay. The centroid of the domain. And so our integration domain here goes from x is equal to 6 to x is equal to 10. Midpoint between these 2 points is x is equal to 8. Okay, so 8 is right in between 6 and 10. And so if you want a formula for the midpoint, xc, this is simply just going to be a plus b divided by 2. Okay. And so if you plug in 6 and 10 here, so a would be 6, b would be 10. You have 6 plus 10 is 16, divided by 2 is 8. And then we have the length of the domain. And so the length of the domain here is just the distance between 6 and 10. So we have 10 minus 6 is equal to 4. Okay. And so with all that information, let's go ahead and evaluate our integral using trapezoidal rule. And so the integral from 6 to 10, 4x plus 6, this is equal to our integrand, 4x plus 6, but we're going to evaluate it at the centroid. And so this will be 4 times 8 plus 6. Okay. And then we're going to multiply by the length of our domain. This right here is f, xc. This right here is b minus a. Okay. All right, so let's go ahead and evaluate this. We have 4 times 8. 4 times 8 is 32, plus 6 is 38. 38 times 4 is 152. Right, and so you can see the answer that we get using from the normal way and the answer that we get from the trapezoidal rule is the same. Right? And so this kind of, hopefully shows you that trapezoidal rule it works, okay? For certain cases. Any questions on how we use the trapezoidal rule there? All right, so you're thinking, wait a minute, that can't be right, right? And so, you may still be skeptical of the trapezoidal rule, as you should be. And so you may, maybe you're accusing me of picking an example that just it happened to work out, right? So let's do another example, and I'll show you that it still works out for that as well. Okay? And then after that, we'll talk about the limitations, because obviously this is not going to work all the time. Okay, so let's do a 2D example. And so let's take a double integral. And so we'll take a double integral from 0 to 2, and then an integral from 0 to 4. Okay. Let's do a very simple function. Let's do 3x y dx dy. This one's not in my lecture notes. I'm winging this one, so it has to be simple so I can get the solution. Okay. All right, so let's do this the normal way. So let's go ahead and apply, let's integrate an x first, okay? So we're gonna apply the integral from 0 to 4 of 3xy dx, okay? All right, so we take that inner integral there. We take the derivative of 3xy with respect to x. We get 3 over 2 x squared y. Okay. We're going to evaluate this between x is equal to 0 and x is equal to 4. And we still have our outer integral. So our outer integral here is 0 to 2 dy. Okay. We'll do the y integral in a second, but let's integrate out the x first. Okay. All right, and so if we apply the x integrals there, we have 3 over 2 times y. I'm just going to factor out the y as well because that's just a constant. Okay. And then we have 4 squared minus 0 squared. All right, so 4 squared minus 0 squared, this is going to be 16. And so we have the 16 divided by 2, this is going to become 8. And so this integral is now integral from 0 to 2 of 24 y dy. Okay. Okay, so let's go ahead and evaluate this integral. And so this integral here is going to be 12y squared, evaluated between y is equal to 0 and y is equal to 2. Okay. So we plug that in, we get 12 times 2 squared minus 0 squared. 2 squared here is 4. So 4 times 12 is 48. So that's the value of this integral evaluated the normal. Okay. Let's do the same thing, but let's evaluate it using trapezoidal rule. This time we're going to use 2D trapezoidal. So let me go ahead and write the integral again. So it's integral from 0 to 2, integral from 0 to 4, 3xy, dx, dy. Okay. So we're going to evaluate this using the trapezoid. Okay. So first, let's extract our integrand. And so our integrand here is 3xy. Next, let's find our centroid. XC and YC. Okay. So our X domain goes from 0 to 4, right? So that's the X bounds of our domain. And so the centroid between 0 and 4 is going to be 2. So we're going to have 0 plus 4 divided by 2 is 2. Okay. And for YC, the centroid of that is going to be 0 plus 2 and divided by 2, which is 1. So now let's compute the area of the domain. And so this one is a little bit trickier, but but it's actually pretty simple. And so our domain looks like this. Where X goes between 0 and 4, and our Y goes between 0 and 2. Okay. And so we have a rectangle where the length of the rectangle in the X direction is 4, the height of the rectangle is 2. Okay. And so the area 4 times 2, which is 8. Okay. So now that we have the area, now that we have the centroid, let's go ahead and plug it in. Okay. Trapezoidal rule says that the integral of this is going to be f of xc yc times the area. Okay. So we plug that in. our integrand here is 3 times x times y. So we're gonna have 3 times xc is 2, yc is 1, and then we're gonna multiply by the area, which is 8, okay? Okay. And so if we evaluate this, we have 3 times 2, which is 6, times 1, which is still 6, times 8, which is 48. And thank God these two get the same value. Sometimes when you're making up examples on the fly, sometimes it doesn't work out, and then you kind of scramble. But thankfully, this one was it worked out pretty well. All right, any questions on how we did that that example there? Okay. All right. So the trapezoidal rule isn't magic, and so it doesn't work for all cases. It worked for these two cases because I picked them to work out. Okay, but the trapezoidal rule does have limitations. So the trapezoidal rule, really, we can think of it as it's only an approximation of the integral. It works best, trapezoidal rule works best when our integram is a linear function. The further away our integrand strays from a linear function, the more inaccurate trapezoidal rule will be. And so if I were to choose, let's say a cubic function. So for the last example, maybe we did 3x cubed times y, then what you'll see is that our trapezoidal rule won't, it won't give us a correct answer for that. Okay? It won't be bad. And so, it'll still give you a decent a number, but, it's not going to be strictly linear. Okay. All right, so there's one last thing I want to cover today before we head out for spring break, okay? And that's this idea of how we actually apply this, and just some practical details. Okay? In particular, I want to talk about 2D finite volumes, kind of in the context of what we're going to do. In particular, I'm going to look at the case of a rectangular cell, which is going to be all the cases that we're going to be looking at in this class. Okay? And so just because of the way that we break up our domain, and we really only work with square domains in this class, we're going to end up always with rectangular cells. Okay. And so in particular, I'm going to look at the case where when we apply divergence theorem around a rectangular cell. Okay. And if you recall, when we apply divergence theorem onto a 2D object, we get a line integral around the exterior of that object. Okay. So let me kind of draw it so you can visualize it. So here's our rectangular cell. And so normally we start with a double integral, right? So normally we start with a double integral. Let's say this is the divergence of K gradient of B dA, okay? That's essentially what we're going to get when we apply the finite volume method to 2D conservation. Okay? And since this is a double integral over the area A, we're essentially going to be integrating over this entire surface right here. Right? But when we apply divergence theorem, we're not going to be integrating over the entire 2D region anymore. Okay? Instead, we're going to be integrating around the exterior of this rectangle. This would be like integral, an integral around the boundary of A of some vector field dot product with them all. Yes. Okay. All right. There's a few features of this line integral that I want to kind of highlight. Okay. The first is the fact that we're taking the line integral around an object that has sharp corners. Right? And so when we go around the sharp corners, it actually becomes hard to do it, to have like a curve that goes around the corners like that. Okay. And so what we typically do is that, even though we have one line integral here, we typically break this up into each side of the rectangle so that we don't have to worry about going around the corners. Okay. Okay. Kind of the requirement of a line integral is that you have to have kind of one curve that kind of goes around the entire thing. And when you have sharp corners, or just whenever you have kinks in your curve in general, it becomes kind of difficult. And so the best way to represent this is through a discontinuous function. Okay. And so what that turns into is that instead of one integral that goes around the entire exterior, break this up into 4 integrals. And so, if I call this, if we use, I'll just use numbers. And so we'll call this side 1, we'll call this side 2, side 3, side 4. Okay. Individually, if we look at the line on side 1, that's just a regular straight line. Okay. Same thing with line 2, line 3, and line 4. Okay. And so if we break it up into 4 contributions and then we add them all up together, we don't have to worry about getting one curve that goes around the entire cell. We just do each 4 individually. Okay? And so what this looks like is like an integral around region 1 of gradient of phi n hat ds plus integral around region 2 or section 2, I should say segment 2. Segment 3, yes, That's segment 4. Okay. So our one integral kind of turns into 4. And I will say that that in general, at least from the last, 3 times that I've taught this, this is the part where people find finite volumes to be a pain in the ass. So, you're doing 4 integrals now instead of 1. And so, for the final project, if you're an undergrad in this class, you'll have the choice of whether you want to do the final project with finite differences or finite volumes. The majority of students do it with finite differences because doing this part here becomes a pain. Especially once you have convection, we add diffusion and convection. We do things like upwinding in finite volumes, and then we add boundary conditions to this. So this quickly becomes a pain, and then the codes actually become very difficult to follow. So that's one thing that we have to kind of take into account. Okay. All right. Any questions on this right here? Okay. So the last point I'll leave you with, before we go, is kind of this other aspect of this line integral here, is the fact that we're taking a derivative or taking a dot product with the normal vector. Okay. And so that normal vector n hat, the way it's designed is that it's designed to point outside of the cell. So if we were to draw kind of the cell one more time. The normal vector, the normal vector, normal vector, vector. Okay. And so the normal vector is another reason why we kind of break up the integral, because the normal vector changes direction depending on which side of the square. Okay. Okay. And so when we're integrating something that has the dot product of the normal vector, one way that you can think about it is that we're integrating, or we're totaling the amount of phi that's crossing the border of the cell. And remember, phi is our generic solution variable. So if it helps, think of it as heat or temperature. Okay. And so what we're really computing here by the line integral is, we're computing how much heat actually crosses the boundary of the cell. So in other words, how much heat is entering the cell, how much heat is leaving the cell. And so our integral, I'm just going to write its generic form here. So our integral of gradient of phi m ds. Okay. Because it kind of has that interpretation of computing how much of our quantity enters or leaves the cell, these types of integrals have a special name. And so we call these types of integrals flux integrals. Right? So everyone in this class has taken heat transfer. And so if you remember from when you took heat transfer, we talked about this idea of a heat flux, right? So heat flux is how much energy or how much temperature crosses a boundary, whatever boundary that you're looking at. Okay. So mathematically, this is how we represent it. And so we represent it as kind of this line integral, or in 3D as a surface integral over a cell. Okay. And this property here, the fact that we have flux integrals kind of built into the method, this is why finite volumes is so popular with fluids, because when you're simulating fluids, incompressible fluids especially, so if you're talking about like liquids like water, the most difficult problem you're going to have is making sure that you conserve mass, which sounds like a very simple thing, but it's actually very difficult to do. But the nice thing about finite volumes is because it's formulated in terms of these flux integrals, you satisfy conservation of mass, you satisfy conservation of energy, conservation of momentum, everything is conserved just automatically, just based on the formulation. And that is really valuable. So, if you look at kind of all of the codes that are out there, all of the commercial codes, open source codes, I don't think I can think of one where there is like a fluids code or a heat transfer code that's written in finite differences. Because in finite differences, it's very difficult to get, conserved quantities. But there are a lot of finite volume codes out there because of this property, conservation of everything, basically, just automatically. And that is very, very valuable. Okay. All right, any final questions before we wrap it up for today? Okay, all right, so that's all I got for today. So thank you guys for coming today. I know the class before the spring break is always a little bit hard, so I appreciate you guys coming out. But whether you guys are here or not, I have to be here, so it's always nice to have company. So hope you guys have a great spring break. Stay safe out there. I know the weather's probably still going to be stormy and stuff, and so if you're going to be traveling, make sure you're careful, right? Get new windshield wipers, and so make sure your car's all checked out and stuff like that. Right? So have a restful winter break. Have a great winter break. And I'll see you guys after the break for more of the stuff. Russell. Thanks, you too. Thanks, Abraham. You too. Hey, Dominic. Have a good break. Thanks, you too, Ozzy. Anthony.